extracellular vesicle isolation by flow cytometric sorting, and characterization by analytical ultracentrifugation and dynamic light scatter. This presentation is from data from Carly Ross and Dr. Thomas Sermine from Beckman Coulter in Fort Collins, and Isaiah Morales Caristrana and Jennifer Jones from the vaccine branch at the National Cancer Institute in Bethesda, Maryland. What are extracellular vesicles? Extracellular vesicles include exosomes, activation or apoptosis-induced microvesicles, and apoptotic bodies. They are secreted from membrane vesicles and are generally heterogeneous in size and composition. Exosomes, in particular, are 50 to 100 nanometers in diameter, and they have several functions, including from immune cells. They can use direct contact, endocytosis of vesicles, and vesicle-to-cell membrane fusion. Why flow cytometric sorting with extracellular vesicles? Size and the fluorescence selectivity allows us to separate unique populations. Using downstream activation and lineage studies for clinical applications, and also high throughput analysis and sorting at the particle level. But you have to have instruments that have high-speed electronics, sensitivity in the forward scatter and side scatter parameters. To isolate extracellular vesicles from HeLa cells, first we grow the cell culture into log phase. Then we remove the media, we rinse it, and we replace it with exosome-free media. We incubate for 2 days, and then we harvest the exosomes from the media using a 3-step centrifugation process. Then we stain with PKH 26 and 67 using the manufacturer's protocol. The MoFlow Astrios EQ side scatter detection limits. The optical engineers from Beckman Coulter in Fort Collins and Miami determined the Me scatter modeling of polystyrene beads using 200, 300, and 500 nanometer beads and an index of refraction of 1.6. They ran these on the Astrios EQ and they analyzed them according to Me theory. The next few slides show the Formomax polystyrene beads acquired on the MoFlow Astrios EQ. The noise population is clearly visible on the 488 side scatter histogram and the forward scatter versus side scatter histogram on the right-hand side. Throughout the next slides, the noise and bead population will be shown in the 2 regions indicated here. There is very little noise in the bead population region, with 5% total. The 58 nanometer beads are in and above the noise. There are some issues with swarming, which will be discussed later. However, the populations are still visible. The 81 nanometer polystyrene beads are visible above noise with a clear population on the forward scatter versus side scatter and the side scatter univariate histogram. The 100 nanometer beads have a mean of 99 versus the noise of 5 median channels. The last few slides demonstrate that the Astrios EQ is able to detect polystyrene beads to 80 nanometers above noise. In this video clip, I artificially created swarming to show the effect it can have on the forward scatter and side scatter of the exosomes by boosting the sample. After stopping the sample, the noise population is visible on the forward scatter and side scatter. When the lasers are shut off, the population diminishes further. The next video demonstrates sidetrack. With zoom, this is a complementary feature of Summit for the small particle sorting of distinct populations.
Setting up the MoFlow Astrios EQ for less than 1 micron particle detection. First, align the stream and the forward scatter with 3 micron alignment beads. Replace the ND filter with a 0 ND filter. Change the mask to P1. On the instrument touchscreen panel, select the 561 side scatter trigger and then adjust the threshold to 0.006%. The noise events per second should be around 5 to 10,000 events per second. If necessary, reduce the voltage on the 561 side scatter parameter. Select the 488 side scatter parameter from the parameter selector, adjust the noise to visualize the population above noise, and then start the sample. Gently boost 0.1 psi increase until the 200 nanometer beads are visible above noise on the forward scatter versus side scatter.